Yeah, thank you, Noam. I hope you can all hear. I often have trouble with my mic here. Yeah, so my intention today is to give you a new definition, a new toy, some motivation, some examples, a couple of theorems, and some open problems. So yeah, they're called Cayley monoids. They are monoids, of course. And the motivation is this. Church formulated Lambda calculus as a semigroup in 1937. Actually, I think it was 36. With eta conversion as a monoid. Conversely, it's very natural to ask when a monoid can support an application operation. That's I intend to try to give an answer to that today. Indeed, Dana talked about viewing combinatory logic as combinatory algebra, so let's try that. I'm going to try that with the notion of a Cayley monoid. Everyone is familiar with Cayley's regular representation of groups in the symmetric group. It's clear that that applies in a limited way to monoids. That is, you don't get actually regularity, but you do get a faithful representation. The notion of a Cayley monoid is just an internalization of that type of representation. So here we have Cayley meeting church. That's Cayley. So a Cayley monoid is a monoid structure, M, product, identity, with two distinguished elements and two maps. So that's the monoid. A and B are elements of M. They could be equal. And A and B are maps from M to M, satisfying the following nice symmetrical axioms. Yeah, let me skip ahead to the next slide to it'll be easier to understand what these axioms mean. So for every mapping, sorry, for that's a typo. I thought I got a lot of typos. Okay, for every little x in M, we can define a mapping, capital X. So the capital X of U is simply A applied to X, product B applied to U. Okay, so the function that we're associating with the element little x is capital X. Okay. Coming back to these slides, you see these four axioms are about those functions. So the function associated with little a returns capital A of X. The function associated with little b returns capital B of X. The identity is the identity. That's just simply saying that A is a left identity for B. And it's a homomorphism with respect to the product and the monoid. Nice, symmetrical, easy axioms. Okay. Examples. Well, of course, there's, of course, the trivial example always. Everything's the identity. And then, of course, the map associated with little x, that is capital X, is simply product. That's Cayley. All right, but the Cayley will appear in a different way as well. So let me repeat. For little x and M, I associate a mapping, which is simply this. But there are a lot more examples that are somewhat similar to the first one. So if I have a monoid M, and I look at the group of the monoid, the group is the set of doubly invertible elements in M. Okay, in a lot of cases, it's big. In some cases, it's very small. And G hat is the inverse. That's the easiest way for me to write it here. Then I can say A of X is multiplication by the inverse. B of X is multiplication by A. Okay, and just as an example, when we get a Cayley monoid. Yeah, if you look at the definition again of this mapping, that's A times U times X. That's A inverse times that. So what we're doing is conjugating X by G inverse. Concrete example. Get a lot of interesting examples from maps from the reals into the reals. here's a nice big monoid with a nice big group. Take the almost isometries. So take vectors in the plane, E's Euclidean distance from V to U, and we say F is an almost isometry if it's almost an isometry. That is, it's an epsilon such that the values are not too far away from the arguments, and it's almost onto. You need that, of course, in the case of almostness. You don't need that in the case of being an isometry. The almost isometries form a monoid under composition. That's quite easy to verify. It's got a very big group. In that group, for example, are the you can blow up a vector or cut it down. You know, we're contracting here. So let A of U be half of U, and B of F be yeah. Remember, A's and B's are maps here, and capital A's and capital B's are maps of maps. So let's do little b first. Let's just blow it up by a factor of 2. And of course, A is the inverse. We're in the group. And the elements do the same thing. Okay. Very good. So there are a lot of Cayley, an awful lot of Cayley monoids just under those definitions, but we're looking for something a bit more. So let O be a subset of M. The Cayley monoid K is said to have an autonomous commutator relative to O. If there's an element C such that whenever X and Y are distinct members of O, okay, well, so if we're thinking of this as the application operation, C applied to X, then applied to Y is the same thing as Y applied to X. That's the way we should be reading it. Okay. Now, of course, in a group, there's a commutator for every pair of elements, but you see C here does not depend on X and Y. That's why we call it autonomous. It's relative to O. We'll be interested in the case when O is all of M, and that's very rare. But one of the motivating examples was the following. So take the group of quaternions. And I've labeled them PQ and R minus Q minus Q minus R, I and minus I, because there's just too many uses for the letters I, J, and K. So it doesn't matter which ones they are, as you know. So that's I, J, and K. So let O be the set, this set, the generators. And we have the autonomous commutator property for C in this case being -1, minus I. This was sort of the motivating example. I realized, in fact, that you could have something like an autonomous commutator. In this case, it's when you multiply them the opposite order, you get minus the first. Oh, example 1. Where's example 2? It is example 2. Okay. Yeah, example 3. This is a bit more of the normal case, I think. So let be the M be the monoid of all functions from the set of non-negative reals to itself. As an example 2, I'm going to take a group element and conjugate by it. Let's just take, add a positive integer to a function. And now I'm going to define the set O to be the set of mappings from the non-negative reals onto an interval between two integers, one onto, order preserving, homeomorphism. Okay, so that's it. I guess that's an example, one way to do it. Take those to be that to be the set O. Now C is defined as follows. Well, the point is that if C sees a composition of two of these things, it knows what the two are. Okay. So it simply solves these equations and then reverses the order. If you like recursive functions, and I guess this will be our first good, interesting example where there's open. Yeah, if you take any pre-complete Airshov numbering of the natural numbers, where the equivalence relation is complete for a jump of 0. I realized in doing this that I didn't know very much at all about arbitrary pre-complete Airshov numberings. I knew something about some of them, some particular ones. So I need to make this condition in the example, even though I'm not sure whether it's necessary. For all I know, there are pre-complete Airshov numberings of every RE degree. I just don't know that. And maybe somebody, so that's number one question. And take the monoid of morphisms that supports a Cayley monoid, where there is an autonomous commutator. Okay, so now that's not so easy to prove, actually. So I'm not going to give any hints about the proof of that. It depends on an old theorem of Myhill's, and it essentially uses completeness for 0 prime. So yeah, the general case for that, for Airshov numberings is, I just don't know the answer. So there's a number of examples that, good. So the existence of an autonomous commutator is, especially for the entire monoid, they don't happen very often. Second definition, in a Cayley monoid K, B is an endo if it's an endomorphism for the monoid. It could also, there's also a limited case of when it's only for the semigroup. I won't talk about that. That's interesting, but it's a little bit aside from the point. Okay, example 5. The Freud-Heller monoid. It's been rediscovered many times. It's the positive part of Thompson's group F. It can be presented, the easiest presentation is on the infinite set of generators B sub n, where for natural numbers n, the relations Bn plus 1 times B sub k, where k is less than n, is Bk times B sub k times B sub n. Multiply, if in the group, multiply on the right by B sub k inverse, and you simply, and it's a little easier to see. Bn plus 1 is Bk conjugated by any of the previous Bk, where k is less than n. But this is also the presentation of a monoid. I'd like to make it a little bit bigger. Let's add the left inverses an, but not right inverses. I'm not going to get the whole group. So I have a nice monoid where half the generators have left inverses. And of course, you have to put in the inverse generators here. Generate the relations, inverse relations. Not yet a group F, but another monoid M. Now, I'm going to make it into a Cayley monoid where B is an endo. So you define capital B, the mapping, to be the next one up. And similarly for the left inverses, it's the next one up. Then B extends to an endomorphism. That's got to be proved. I mean, it's not automatic given those relations. And indeed, given these relations, each element can be written uniquely in the following form. B of D, where D is an arbitrary element in the same form, including I. By the way, B of I is I. Okay, so B to the K times A to the L. This part here, you might recognize as the, if you know anything about semigroups, I don't know, semigroup theory is quite chaotic. But this by itself is what's called the bicycle monoid, and it occurs very often in this context. This is a bit more. All right, so these normal forms are unique, and that requires proof as well. More about that later. At any rate, if that normal form is unique, then indeed what we do is we can define the Cayley monoid where B is B, and A is simply you wipe off the capital B, and you kill that part of the bicycle monoid that's at the end there. So A of BD is capital D. Now in this Cayley monoid, you can recover the product from the application operation. It's just exactly this. This looks like in lambda calculus, if B is the lambda term B, capital B, Cayley's B, sorry, too many names that begin with C here. Curry's capital B, B applied to X applied to Y is the combinator semigroup star. So we recover it this way. Now, if the relations of M are realized, the relations of M can be realized in linear lambda calculus under beta-eta conversion. So this is what we want to say. This is the relationship to linear lambda calculus in particular. So B is B, and A here is the combinator C star star. Too many stars. It's C applied, the combinator C applied to I, which looks like this. It's a left inverse for B under eta conversion. Yeah, let me mention everything I say here is going to be using eta conversion. Comes quite naturally here. The semigroup operation is application of B. Okay. Indeed, we can interpret the relations up here in that way. They're all validated. All of this is validated. Then we have indeed these normal forms exist. Okay, and it's quite easy to prove that the normal forms are unique for lambda terms. So it follows that they're actually unique for this.
Rick, could I stop you just here, just ask a question about this example? So I mean, here you're realizing a Cayley monoid by lambda calculus, and so I mean the elements correspond to lambda terms. Could you say like what lambda terms, if you consider all of the monoid, what I mean? I see that these are ordered linear lambda terms.
Yes. Oh, you don't get all linear. You do not get all linear lambda terms at all.
But do you get all of the ordered linear lambda terms, or not all of them?
You get all the what? Yes. So what's missing? You get. I'm not sure what you mean by ordered.
I mean that yeah. Go ahead.
It's a submonoid of the linear monoid. There are two generators that are missing. The generator that's missing is excuse me. BC, B of C. Yeah,
so you have B.
You only have CII. You don't have C. You don't have CI.
Yeah.
You only have CII. Yeah. So this is only a yeah. There are two of the four. You need to generate it. You need B. You need C, and you need C of C and C of B, and of course the identity. Yes, it's the two that are missing. So the answer is you're only getting a submonoid of the monoid of all linear lambda terms. However, we're not done yet. Okay, we'll get them all in a minute. Yeah. So below we shall refer to this Cayley monoid as RAP, Richard, Thompson, Alec, Peter Fried, and Alec. So in RAP we have these two axioms. A is a left inverse for B. Now, if we go on and look at our representation of RAP in the linear lambda calculus, okay, we also get the following. These are true axioms. Okay, these are indeed true axioms of linear lambda calculus that are not realized in this monoid. One's interesting, we'll come back to one. 2 through 6. All right. These two were observed by Church in his proof. I noticed this one years ago, and this one just falls out of the proof. So now we have some examples. Let's go on to some theorems. Theorem 1, if K is a Cayley monoid with the endo property and an autonomous commutator, and the axioms 2 through 6 hold, you get one for free. I'm just going to say. Then K contains a copy of the full linear lambda calculus with B equals B and J equals C. The autonomous commutator is indeed. Yeah. Now note that I never said that the Fried-Heller monoid, that Alex Heller, by the way, Fried-Heller monoid has an autonomous commutator. It doesn't. But if you assume that there's an autonomous commutator, which you do have in the case of linear lambda calculus, and it is C. Okay. Well, who's J? Yeah, did I define that in here? J is in fact C applied to I. Yeah, it's C applied to I. Lambda x y y x. How's that? I'm sorry that wasn't defined here. That came from a previous version of these slides. Okay, so J is in fact lambda x y y x. So if you have a Cayley monoid with endo property and an autonomous commutator and these axioms hold, then K contains a copy of the linear lambda calculus. There's your new toy. Okay. The proof. Okay. Proof consists of two parts. I'll only describe it. I'm not going to try to put the details up here. It's like an axiomatized version of chapter 7 of Barendrecht's book. You have to verify that B and C have all the given all the necessary properties. Okay. And then you define abstraction using B and C. But we're going to verify eta conversion. Okay. Eta conversion is very, very easily verified. So the combinator theory becomes the same as the lambda theory. Good. With all these axioms. That gives us a homomorphism of linear lambda calculus into K. For faithfulness, we need a version of Bohm's theorem for linear lambda calculus. Now, there's an awful lot known, especially in Paris, about Bohm's theorem. And I didn't know, I couldn't find a version of Bohm's theorem for the linear case. This is very, very strict. It's linear and it's lambda I calculus and it's linear. Every variable occurs exactly once. There may very well be a known version of this, and if anybody knows of one, please tell me. I have to verify this myself. But that certainly, there is such a theorem, and it verifies that the homomorphism is in fact faithful. So in fact, you get a copy of the linear lambda calculus inside of any Cayley monoid, satisfying 2 through 6, endo property, of course, and autonomous commutator.
Just to back up, just another question. Again, how is application defined for the Cayley monoid?
Yes, application is defined. Yeah. Let me go back to, yes. Let me go back to the first slide. Yeah. So now, yes. Yeah. Application of X to U is A, X star B applied to U. That's application, the application operation. Okay. And that is in lambda terms, that's the application of CII, C star star, okay. X, the usual composition, and this is the application of BDU. So in lambda terms, it would be C star star applied to X, composed with B applied to U. And that is equal to, with eta under eta conversion, X applied to U. That's where the definition comes from.
Okay.
Okay, yes. So I know it goes by very quickly when you first see it, and you don't realize that that's really what the application operation is. Okay. Okay. So that's, yeah, that's theorem one. Theorem two. This is a little bit, yeah, this is kind of interesting as well. Every monoid altogether can be embedded into a Cayley monoid with the endo property and an autonomous commutator, and 2 through 6. Okay. I just want to add that at the end. This is not so exciting, really. We embed M into the lambda calculus I can use the Hindley-Rosen theorem. So what I'm just going to do is take this monoid and I'm going to add it in as a system of rewrite rules to ordinary untyped lambda calculus. And that's okay. But that does answer this question. Every monoid can be extended in this way. Of course, I'm not saying that if you give me a Cayley monoid, I can extend it this way to a full copy of the lambda calculus, preserving all of the Cayley monoid structure. I don't know that. I don't know what happens if you try to add, for example, if you had a Cayley monoid looking like this, what happens if you try to add the combinator M? Mx equals, oh, sorry, M is lambda x, x applied to x. I don't know what happens there. You certainly can have such an extension, but it may not be preserved. Okay. Well, there's a lot of problems. Pretty much any question you ask, I don't know the answer to. But the main problem, I think, would be the following. And I've asked some of my set theoretic friends about this, and no answers yet. Suppose I take all functions from the set of reals to the set of reals. Okay. Can we define a Cayley monoid structure on that monoid with an autonomous commutator? I really doubt it. But I'm not. I sure don't know how to prove it. So, hope I didn't go too quickly. Oh yes. Now, some of my. Yes, I see some of my references have disappeared. I don't know how to get them back.
What are 1 and 2?
Pardon?
What are 1 and 2?
Yes, well, 1, of course, is Barendrecht. But 2 is Berger. Berger has 2 papers on Thompson's groups and Thompson's monoids, and they're certainly worth looking at. And that's my last slide.
Okay. Thank you very much.
Okay. Yeah. Okay.
Okay. Are there questions? Are there questions from the audience, either here or online? And if you're online, please raise your hand so that we can notice you. Yes, there's a question from Peter Hines. Maybe can you go up to one of the laptops?
Is this okay?
Oh, wow.
Okay, now I no.
Yeah, do the sheet.
Computer.
There you go. No. Okay.
Okay, again, without the funky sound effects. So it's a categorical question, if that's okay. So essentially, traditionally, Thomson's group is associated with coherence for associativity, whereas Cayley monoids, we think of them as axiomatizing some form of closure. So the question is, what is it about moving from the monoids to the Fried-Heller, sorry, from the group to the Fried-Heller monoids that moves us from associativity to closure?
I'm sorry, I'm really having trouble hearing.
This isn't necessarily a very well-defined question.
I had a lot of trouble hearing the, so we want to know about the,
Okay, yes, I can be here.
Okay, how about you come over here to speak?
Okay, we're going to try again.
yeah, I know. I don't hear too well anyway, so,
Okay. Yes. Hello.
hi.
Hi. Okay, good. This is working. Great. So the question is, it's a categorical question. Traditionally, we associate Thomson's group F with associativity, whereas Cayley monoids we associate with some form of categorical closure. So the question is, what is it about taking the positive part and moving to the Fried-Heller monoids that lets us recover some form of closure from associativity laws?
I'm sorry, I just really can't hear the exact problem.
Should we give up on this because it's
Yeah, or maybe you can write him afterwards.
yeah, okay. I shall send you an email. Thank you for a very nice book.
Please do. I think I've had trouble with the sound on this particular laptop I'm using, so that may not be helping very much.
Okay.
Please send me an email. Thank you.
Yeah, I'll try to ask one question, and then if not, I'll write to you afterwards. But just to understand where the definition of the Cayley monoid comes from, could you speak to that?
Where it comes from. I thought of it in July. It comes from, as I said, I'm going to provide you with a new definition. It's a new definition.
But
as far as I know, it does not occur anywhere in the literature previously. I tried to answer the question for myself. When does a monoid support an application operation? I didn't want to go nearly as far as saying I wasn't interested in reflexive categories. I wasn't interested in reflexiveness. Just simply wanted to support an application operation. And the first thing I thought of was, well, I know an example of where in very elementary algebra where that sort of thing is done. It's in Cayley's theorem. Every element gets mapped to the left multiplication. So that's where the definition comes from. As far as I know, it doesn't occur in the literature. Yeah.
Okay, but you were thinking of combinatorial algebra.
Yes.
Yes.
Absolutely.
Yeah.
Yeah. I mean, I said, well, how is the monoid in Lambda calculus related? Well, you apply B, and then you apply C star, which is its left inverse, and it comes out to be exactly, yeah.
Okay.
I don't know if that's a satisfactory answer, but yeah. Then I saw that there were examples.
Okay. Are there other questions? Okay, if not, then thank you very much for the talk. Let me stop the recording.